then the area of that slice is just y delta x, very much like the rectangles. And the mass, therefore, is mass times area, so it's my delta x. And then the moment of that slice about the y-axis is its distance from the y-axis, which is x. So the moment of that slice is x times my delta x. So we've found the moment of a particular slice. In order to find the moment of mass of the whole sheet, we now sum all of those moments together. And that gives us the sum over the region we want from x equals 0 to x equals a of xy delta x. So that's our sum. We then take the limit as delta x tends to 0, and we know that that, by definition, gives us the integral between 0 and a of xy dx. Y is 2x, and so if we substitute that in, effectively all we need to calculate is that integral. The integral of which is constant, times 2x squared. That's quite easy. It's just x cubed over 3, you take out the 2m, which is just constant. You evaluate between the limits, and we get 2m a cubed over 3. So now we've got the moment of the total mass, and now we've got the moment of the mass. So we equate those two, and we can find x bar. Just 2ma cubed over 3 divided by ma squared, so it's 2a over 3. Okay? Some of you may have known as a third of the length, if you like. So, 2a over 3 is the distance, and notice here that the masses cancel out. You're just looking for a length here. Okay, so although we've used mass per unit length to get to this point, effectively that all disappears. And you should always check the answer you get, you've got the right dimension. This is just a single a, single length, which is what you'd expect. If you get an a squared or an a cubed, then clearly you made a mistake. Okay? Always check dimensions. So what we've got here, again, is the same principle. Moments of the mass divided by the total mass. Now we found x bar. To find y bar, there are two different possibilities here for calculating it, and you can choose whichever one you prefer. They're both very similar. In the first case, to find y bar, okay, in other words, the distance of the centre of mass from the x-axis, then we know that for each of the slices that we chose before, that the centre of mass of each slice must lie halfway up it if it's uniformly distributed in terms of mass. So that's y over 2. So suppose that all the mass of a particular slice acts at that point. Then the moment of the slice about the y-axis, if the centre of gravity is at y over 2, is y over 2 m y over 2 delta x. We sum all of those slices, we get, in terms of x, the sum from x equals 0 to a of my squared delta x. Take the limit as delta x tends to 0 again, and that gives us an integral, my squared over 2 dx. Because we're integrating with respect to x, okay, we know that y is 2x, so y squared is 4x squared. And so here we're doing everything with respect to x, even though we're working out the y coordinate. Again, if you evaluate the integral, evaluate that between the limits, you get 2ma cubed over 3. So, in this instance, for y bar, we know the total mass is ma squared times y bar is 2ma cubed over 3, and hence y bar, which actually turns out to be the same as x bar, 2a over 3. Okay. So, in this case, you can work out the y bar coordinate in terms of integrating with respect to x. The other alternative method is to to take a script in the opposite direction. Sometimes in the application, it depends on the application you've got, which is the easiest method to actually apply. So this is the alternative method for finding y bar. In this case, here's our triangular plate again.